Okay, so then let's jump straight into business for today. So thanks for coming into this lecture, both in person and online. We are getting into week 3 of this course, so ideally things should start, gathering some momentum, and we are warmed up enough to look at hopefully some more advanced aspects of our course. So let us begin doing that. So I will be beginning what we call module 2 of the course today. Of course, we are in this course on the fundamentals of attosecond science and technology, course on fundamentals of attosecond science and technology from IIT Madras and IIT Tirupati. So in module 2 we will go into laser pulses. Laser pulses, specifically we address femtosecond laser pulses. We will gradually work our way there. We are not in a hurry to just jump in and start producing femtosecond pulses, although that would be great, right. So that is this lecture onwards, and we will go into generating pulses, measuring pulses, and so on and so forth. Once more, our textual references are the 3 books of interest which I have mentioned here. The one on femtosecond laser pulses by Roulier. If you have access to it, the students in person should have through the local library, that is institute's library. So in whatever form you can access it, yeah, please find it and get yourself access to the reference material. Those elsewhere, if you can access it through other means, your local resources would be great. So yeah, so the textual references for this section of the course as well are these 3 nice books: Femtosecond Laser Pulses, Fundamentals of Attosecond Optics, and Principles of Optics by Born and Wolf. And as always, thanks to Professor Trebino for sharing his lecture materials and inputs for this course. Since we have also had a few days of a break, I will do a brief recap of our previous lecture. I know sometimes I am belaboring this maybe a tad bit too much, but for any breaks in continuity at either end, we should in this lecture, let us recap a bit of what we did in the previous week, broadly, some of the key results, and then gently glide ourselves into optical pulses. How to formally describe them? We all have our own notions about what a pulse is, maybe, and so on. And then I deliberately want to dwell a bit on one of the, I would say, 2 most important mathematical tools that we will use in this course. One is differential equations, which we have started to use our knowledge of more than anything else. We already have very likely learned this in courses on engineering physics, or mathematical physics or engineering physics, not engineering physics, engineering math, right. So basically Fourier transforms are one of them and differential equations are the other. And then we will move, after refreshing basic notions about Fourier transforms, into the frequency domain. So we will begin with the time domain and we will go into the frequency domain. That is the idea. Okay, first for the recap. We looked at Fabry-Perot cavities, interferometers, etalons, optical resonators, all of which we used synonymously. They are conceptually and notionally the same. We basically understood that after performing several round trips in the cavity, the beam that transmits through its transmittance can be measured and plotted as a function of frequency. Okay. So, that results in the following plot, where you have frequency on the horizontal axis and transmittance on the vertical axis. And at cavity resonances, resonator resonances, which we call the resonant modes of the cavity, at these frequencies we see maximal transmission to unity when in all cases, whereas for various different values of the quantity f, which we defined earlier in our lectures, that is f is, what is it? What is f? Any responses? What was f? Before I write it down. Okay, let us refresh our memory since it is a recap. What did f depend upon? Okay, so somebody, one of our friends has notes, diligent notes, so has given it away. 1 minus r square like that, or 1 minus the square of r, the whole square. Okay, good. Numerator is, okay, and r is, you had something, pardon? Okay. Reflectance of the cavity mirrors or the either end surfaces of the echelon, the two surfaces which form the two reflecting surfaces which form the resonator, and in this case we are assuming that the reflectances are identical, right. It, one could, as I have earlier discussed, have scenarios where they aren't identical as well, but we'll stay with this. Conceptually we don't miss anything significant by making the two reflectances identical, but if we do that, f determines this for the cavity, which is, we basically have sharper cavity resonances, narrower line widths. In all cases, the free spectral range of the cavity, which is essentially the FSR, free spectral range of the cavity remains the same. And what is the free spectral range for the cavity? If nu is frequency, the cyclical frequency, then the free spectral range in this variable is what? Anybody?
Speed of light divided by total round trip length.
C is the speed of light even in the medium. So, we usually use this symbol for the in vacuo speed of light, but let us take that to be the velocity, the speed, magnitude of the velocity, and divided by round trip length. We have used 2L for the round trip length in this course, right? Pardon me? L. Round trip length, did we use L earlier? We will check it out, but in any case, let us, to keep things consistent, let us look at this equation, nu q on this slide, q being the index for the mode, is C by 2L. So, the spacing between any two successive modes, we can read it off from here, and consistent to this formula, equation rather, we have on the board, this is the free spectral range of the cavity. Okay. And this is how the waves standing in the resonator look like. Q1, 2 has two wavelengths, in a round trip, 3 has 3 wavelengths in a round trip, 4 has 4 wavelengths in a round trip, 5 has 5 wavelengths in a round trip, and 6 has 6 wavelengths in a round trip. Okay. And the bottom here is the experimental realization, a view from the experimental realization, where on the horizontal axis we have the frequency is swept, and on vertical axis we have in transmitted intensity or signal. Okay. So, that is basically in one view graph the vital statistics of a Fabry-Perot interferometer or optical cavity of the kind that we have considered. The next thing we looked at was the following, and we had this sort of insight, as we have called it, wherein we said that the real world sort of spectrum of the transmittance which we saw has these features. Essentially, it is going from the spectral to the temporal domain, because that is what it is. Each of these cavity modes occurs at a resonant value for the frequency omega. Again, pardon me for this, the W here should be omega, but I have this font issue, if you remember. So, at particular angular frequencies where we have plotted, we have these spectral peaks for the resonance. These are the modes, and in real life, as we saw, this is modulated by some physical envelope. Okay. The line shape of each peak is described by this function g of w, or d of omega rather, and the envelope has the shape f of omega. Of course, one too many f's. So, let us be alert to what they are. The f here is the Fourier transform of the capital F here is the Fourier transform of the little f function, which we are going to which we have spoken about and we will speak about now. It is not the number f of the cavity. Okay. So, so this is the shape of the cavity resonance, but then we need a third function to capture the periodicity of these peaks, which have an identical shape function g in this first level consideration. Okay. So, this function for the periodicity, which we denote by this the Greek symbol, takes care of the periodicity. The periodicity is in the variable omega, and the periodicity is in frequency units 2 pi by t. It is 2 pi by t, it is 4 pi by t, and in integer multiples in either direction. Okay. Now, what did we do? We took this, we said, okay, if the electric field inside the cavity has this functional form, that is at the bottom of this view graph, then these three functions which we have here, capital F, the envelope, spectral envelope, the line shape and the periodicity, right. If these three are the three functions that we are describing, essentially we can get a time domain picture of the same about the status of the wave, the electric field in time, from doing an inverse Fourier transform of these into the time domain. We do not know everything about them as yet. For example, we have not specified the exact form of G. It looks Gaussian, but there is no reason to restrict it only to a Gaussian. The envelope also looks like a Gaussian, but these are all matters of physical detail, and every system that we consider can essentially have its own G and own F and so on. All we know is from the design of the echelon, the spacing between, or the resonator, the spacing between the two successive maxima or resonant frequencies is 2 pi divided by the round trip time. So, nothing else has to be common among different resonators, right. Of course, even the round trip time is particular to the design of the resonator, but then even with this sort of generic view about this shape of this peak, we can draw some pertinent insights, which being that if I were to Fourier transform a function, a 3-piece function of this type describing the spectral electric field or electric field amplitude in the spectral domain, which is the domain of omega, then all I need to know are three pieces once again. First, what is the Fourier transform of the function f of omega, the envelope function from the spectral domain. So, assume that this is even something you measured. So, you can analytically or computationally do a Fourier transform of f of omega. Likewise, you can find the Fourier transform of g of omega, and you can also find the Fourier transform of this periodic function. Okay. All three you can find the Fourier transform of either numerically or in the case of this periodic function also analytically, okay, from its very definition. Once you do that, we then figure out that this shape or this functional form in the spectral domain has a corresponding form in the temporal domain by noting that little f of t, little f of t is the conjugate of capital F of omega, little g of t is the conjugate of capital G of omega or uppercase G of omega, and this is a standard function for the periodicity. Okay. So, we have not played any tricks over here, but then we also note that here between the periodic function and the G, in the case of the spectral domain, we had a convolution taking care of the spectral shape. So, the convolution in the spectral shape between the two functions, the periodic function and G, essentially needs to be replaced by a mere multiplication in the conjugate, that is time domain. A multiplication, once we do this, we obtain the equivalent of the Fourier transform of this product, or rather the convolution of these two functions. Then the product here between these two guys is replaced by the convolution in the time domain. So, properties of Fourier transform, which we will look at shortly, give us this insight. So, what this tells us is that there is certainly a set of physical sort of conditions or realizations possible with the Fabry-Perot interferometer or echelon, where we have the hope of creating a train of identical pulses. Here the train is of course finite, owing to the fact that the spectral amplitudes are also over a finite spectral width. Okay. So, we can indeed have a train of pulses using a resonator like this, and we will need very little less. Conceptually, this allows for itself. So, the fact that I have resonator modes and an envelope and it has this functional form blends into having pulses in the time domain owing to its spectral structure. Okay. So, the light field transmitted by the echelon we would basically admit to the fact that it is a set of pulses. Okay. So, that is to say you have the first pulse tallest, then the next and so on and so forth. Okay. So, remember, maybe if of course, here the amplitude of these pulses is diminishing, you could further gain some insight from the fact that this spectrum with the envelope and so on corresponds to an echelon which we assumed was lossless and fully transparent, with a defined only by a reflectance R and the round trip length L. Okay. In as much as we say lossless, it is also gainless. There is no concept of a gain there. So, I am not using the word, I am not prefixing laser to pulses. Pulses are possible, they are a natural outcome. That is all the statement we want to make. But then if the resonator stores a finite amount of energy and emits a pulse in one round, at the end of one round trip, it has lost the energy stored, and in the subsequent round trip, of course, the overall energy has come down. So, the next pulse emitted is weaker and the whole thing sort of decays. There is a loss at every round trip due to the emitted pulse from the resonator. Therefore, these would appropriately decay as well. If I were to use the resonator to build a laser, we can, it need not be that we have a diminishing train of pulses, a train of pulses with a diminishing amplitude in time. We can maintain a steady amplitude by adding periodically enough energy into the system, which is how a real laser would operate. So, you have a nearly identical finite train of pulses going on as long as the device operates. Next important thing that we also discussed is in terms of the line width of the individual spectral peaks in the transmission. which is the line width of the echelon. The line width of the echelon could be deduced by us from the transmission function T, which is 1 minus 1 plus f. The function f is, as you rightly pointed out, 4r divided by the square of 1 minus r multiplied by sine square delta by 2. Delta is the round trip, the phase accumulated in any one round trip, right. So, this depends therefore only on the reflectance r and L, the round trip length. Now, in order to determine the line width, we did our maths, and it turned out that the line width, essentially I gave you a do it yourself piece to arrive at this expression for the line width, which is in terms of wavelength, it is lambda square divided by pi L. Again, very importantly, it depends on 1 minus r by the square root of r. Okay. So, this is the next important thing, and maybe I should add here by hand that from here we went into defining a quantity called the finesse. Okay. The finesse essentially is we synonymously use line width and FWHM, full width at half max of a particular line. So, in this language we wrote down the finesse to be the free spectral range FSR divided by FWHM of the given spectrum, right. So, that is the finesse of the cavity. It is often, we often write this as script f. As I said, there is sometimes possibly one too many repeated use of the same character, but context defines the meaning. So, optical cavities can come in different shapes, right. So, it could be 2 mirror cavity, it could be multiples of these 3 mirror, 4 mirror, so on and so forth, right. So, but then as we discussed in the previous lecture, there is a formal theory for the stability of these cavities, that is to say, we have computed in the case of the Fabry-Perot interferometer in an infinite sum of wave pieces which define the transmitted wave. So, we are assuming there that the wave stays perfectly within the resonator over a large number of round trips, right. Recall that we summed up the electric field amplitude transmitting after 1, 2, 3, 4 and successive set of round trips, right. So, in this case there we presume that if you wish, even the ray stays forever inside, or the photon beam or the electromagnetic wave stays within without getting lost. That is seldom the case in real life. Okay. So, it is then resonator theory takes over, and you need to build a very good resonator to keep the beam for a sufficient duration inside the resonator without it getting lost. So, for these kind of popular cavities 2, 3 mirror, the V shape for 3 mirrors, the bow tie or set for 4 mirror, or whatever the case may be, right. There is robust implementation of the principles of, in this case, ray optics, which tell us that for the ray itself to be confined to the resonator, of course, we are moving now from the wave description to rays. So, is there a conflict? No, not at all. So, think of k vector, the propagation vector of the propagating electromagnetic wave to be the ray, it is approximately correct. Okay. So, we are not going into details of what is a ray, if you look at it from the perspective of Maxwell's equations and so on. For a more formal treatment of this, please look into the book by Born and Wolf. I think it is even in the early chapter, where you get a nice treatment of rays and the governing equation for rays, right. For example, Snell's law is far too simplistic, it governs just the behavior of rays at one interface, but what if you have other kinds of media and so on, like a refractive index gradient, how would a ray propagate through that, right, and where do you encounter that in, like, say, mirages, how are mirages formed. So, So, there is a refractive index gradient. So, that is a gradient index medium, and it is not going to be easy to apply Snell's law over there, at least analytically. You may be able to still finite difference it through a computer and do stuff like that. But then a good thumb rule is to consider the propagation vector and say that is the ray, which is not entirely correct. There are some nuances involved, but ray typically is associated with the direction of propagation of the energy energy transport direction, okay, which for isotropic media turns out to be the propagation direction. For anisotropic media, there can be a slight, a small angle between the k vector and the Poynting vector, which denotes the direction of energy transport. Okay. Any case, this again, these concepts are very well described in Born and Wolf and other such excellent texts. But then if we, so taking the rays up as a way to think about the waves in a resonator is perfectly legit and very instructive too. So, if you keep the ray inside, you keep the wave inside, that is the logic. And here one can place any resonator that we have considered so far on any creative ones that anyone may design on this so called stability diagram, where we have two axes G1 and G2, where in this blue hashed region, the region where the product of G1 and G2, this is by, you can say, mere inspection of plots, the product of G1 and G2 should be within 0 and 1. If your resonator has a design such that its G parameters, 1 G for each mirror to on the left to the mirror on the right, or each of the two end mirrors, mirror R1 to mirror and for mirror R2, follow this, if G's are defined according to that. So, if, and what are G's? G's were essentially G1 or 2 is 1 minus the cavity length D divided by R1 or 2 as the case may be for G1 and 2. It is a geometric, it is defined through the cavity geometry. Then so long as the product of the G's is such that the cavity falls within or even at the boundary of this blue painted region, your resonator is considered to be a stable one. Although of course, you can imagine that in a stability analysis, you are also thinking about the instabilities, and any small perturbation will lead to these resonators on the edge to fall off. If by design you wanted them to be stable, that would well have been the peril of keeping it there. On the other hand, if you have a design that is like the concave convex, you could well have placed it away from the disputed border of dispute between stability and instability, right. So, that is a good wrap up, I would say, on resonators. So, we have resonators, we have their free spectral range, we have line widths, we have the cavity finesse. The cavity finesse is also the quality factor of the cavity, and then we realize that in order to design a resonator, we can take into account its geometry, take recourse to rays and go forward. By the way, this discussion on the stability of resonators, I referred you to a couple of books. There is the book by Verdian, Laser Electronics, which I like to look into, or also the book by Amnon Yarif, or the books Optical Electronics, I think by Tyagarajan and Ghatak has a good description of this, as also Contemporary Optics by the same authors. All these are good sources, as well as some courses on NPTEL as well on lasers. Please look them up. They our colleagues elsewhere have treated them very nicely. So, you can design a cavity by yourself, provided you have sufficient time and sufficient resources. That is all I wish to sort of convince you, and you can possibly build a good resonator, right. But then we realize that the moment you have a resonator in hand, the electric field inside the resonator naturally lends itself to generating a set of periodic set train of pulses. So, that was the other insight we got. So, now we are armed with enough knowledge and insight to proceed and look at